Okay, we're going to look at frequency and period of wave, and also amplitude and energy and how they relate mathematically. So, frequency, as you probably recall, is how often the particles of a medium vibrate when a wave passes through the medium. So, frequency means how often. We use hertz for frequency. Now, 1 hertz means 1 cycle per second. So, a cycle would be up, down, back up again, right? So going back to the rest position. So if we go up, down, back up again, that's 1 cycle. And how many cycles per second would be our frequency in hertz. A period is just the inverse of frequency. That's how long it takes to make 1 complete cycle. So if it takes 1 second to make that cycle, our period is 1 second. Our frequency is also 1 over 1. But period and frequency are inverses. So if I know one, I just take the inverse and I can find the other. So, for example, we got a wave, and it has an amplitude. So let's try to draw this. It's held into a thin wire at each end. So I'm going to use transverse, and then this is going to be my my rest position. Oh, not too far. Here to here is 3.8 centimeters. The frequency is 51.2 hertz. And a distance from crest to trough, so from here to here, is 12.8 centimeters. And it says the frequency is 51.2 hertz. So if I look at the math of this, and I want to be able to think about it, all I want to look at is frequency defined period. These distances mean nothing in period. Period's all about time. So I go 51.2 hertz, which is per second, to find my period. Period is just 1 over my frequency. So if I go 1 over 51.2, I would know my period in seconds, because hertz means per second. So I do all this math, and it's going to be a really, really small number, as you probably know. I'll go 3 sig figs, and I'll say my answer is 0.195 seconds. So it's just the inverse if I want to find the period from the frequency. Let's look at another one. I Love You Daddy accompanies her father to the park for an afternoon of fun. While there, she hops onto the swing and begins a motion characterized by a complete back and forth cycle every 2 seconds. So she's on the swing. She goes back and forth and back again every 2 seconds. So from her rest point, back and forth and back again every 2 seconds to do that. Okay. And so the question is, what's the frequency of her swing, and what's the period of her swing? Well, her frequency is 1 cycle. So frequency is cycles per second. 1 cycle every 2 seconds. So 1/2. So my frequency is 0.5 second, or 0.5 hertz. The period's pretty easy, right? The period is 1 cycle every 2 seconds, so the period is going to be 2 seconds. 2 seconds to complete 1 cycle. Now, amplitude. How is energy transported related to the amplitude? Let's look at these 2 waves. This is a low energy wave, and this is a high energy wave. First thing I want you to notice, our wavelengths are pretty close to each other. So wavelength has nothing to do when we talk about energy. Amplitude does. And amplitude is distance from the rest position. And when you look at this, the greater the amplitude, the higher the energy. Okay? So the higher the amplitude, the higher the energy. Lower the amplitude, lower the energy. So when we look at a wave, we know that. Now, there's a relationship here, and it's approximately here. Okay? It's energy and amplitude are close. So if you double the amplitude, you quadruple the energy. Okay? So if we double the amplitude, we quadruple the energy. So when we go from 1 unit of amplitude to 2, so we double. We go from 2 to 8, we quadruple. When we go from 2 to 4, we double. And then when we go energy, we quadruple. So if you double the amplitude, you quadruple the energy. Always a good rule of thumb to think about with waves. So we got Macintosh. They're standing 8 meters apart. So here's Mac. Here's Tosh. And they're 8 meters apart. And demonstrate the motion of a transverse wave on a snaky. Okay, so they got a slinky and they're whipping it around. The wave, as it goes up and down and up and down, has a vertical distance of 32 centimeters from trough to a crest. Vertical, that's here, right? So that total distance from trough to crest is 32 centimeters. The frequency is 2.4 hertz. And the horizontal distance from a crest to the nearest trough, so here to here, is 48 centimeters. And we want to find amplitude, period, and wavelength. Wow, this is you're going to be asking for a lot here. So how can we take that information and use it, right? So as we look at this, we want to look at how we can find the amplitude first, since that's first on our list. Amplitude is distance from rest position up, right? Since from here to here is 32, half that would be my rest position. So 32 divided by 2. My amplitude is 16 centimeters. Now my wavelength. Wavelength would be from crest to crest. From crest to trough is 48. That's going to be half of going from crest to crest. So 48 times 2 would be my wavelength. And I would see 48 times 2 would be 96 centimeters for my wavelength. And then let's look at the period. To find the period is just 1 over frequency. So 1 over 2.4, right? And when I do that math, I get 0.42 seconds. And that's my period. So even I took just different information and I could apply it, okay? Something about wavelength there. Distance from crest to trough on the horizontal is half the wavelength. Just like distance from crest to trough in the vertical is twice the amplitude. There's some math there you can use, and maybe making measurements will be easier that way. And of course, period and frequency have their own relationship. Let's look at another example. Ocean wave with an amplitude of 2.5 meters. Weather conditions suddenly change that the wave has an amplitude of 5 meters. The amount of energy transported by the wave is, think of an answer while I draw. So I'm at 2.5 meters of amplitude. All of a sudden I go up to 5 meters of amplitude, so I double. If I double my amplitude, we quadruple our energy, right? Double means quadruple. So it's going to quadruple. The answer is C. Two waves are traveling through a container of an inert gas. Inert gas is just a gas that doesn't react, so it's in a gas. Wave A has an amplitude of 0.1 centimeters. Wave B has an amplitude of 0.2. The energy transported by wave B must be blank the energy transported by wave A. So they're in the same medium. That's what this means. So if they're in the same medium, all things are equal when we talk about speed. So we're not worried about anything but speed and energy here. And we got 0.1. We got twice as much, 0.2. So B must have more energy. And it must be quadrupled. It must be 4 times that of wave A.